Hello and welcome to another live stream from Portland State University's Learning Center. I'm Travis. I'm a chemistry tutor here, and we are going to be talking today about electromagnetic energy. We're going to talk about some electron configurations, a little bit about the Bohr model, and go into quantum theory and different electron orbitals and configurations and stuff like that. So a lot of fun stuff happening today. As always, I'm going to paste some links in the chat. Definitely make sure to follow us on Instagram, Facebook, and check out the Learning Center's tutoring webpage as well. You can also find all the past videos that I've done on YouTube, which is going to be on this following link right here, so check those out. Stay tuned after this live stream, or drop into the Pingy app more appropriately, for a drop-in tutoring session, which is going to last until 5 o'clock tonight. So stop in there with any questions you might have for me, and I'll be there. You could also schedule an appointment with our chemistry tutor, Amir. He does tutoring throughout the week, so you can also schedule appointments with him via the Pingy app. So let's get started on what we're doing today. All right, here we are. This first problem I want to talk about has to do with electromagnetic energy, because light travels as a wave and a particle, and it has a certain amount of energy per photon that is traveling. So we can use the relationships between the frequency and the wavelength with the speed of light to determine its energy, essentially. In this particular problem, we have an FM radio station, which is found at 103.1 on the dial, which broadcasts its frequency at, believe it or not, 1.031 times 10 to the 8 hertz, or per second is what the hertz is. So they want to know what is the wavelength of these radio waves in meters, or standard unit for length and distance. So I'm going to point out the key parts of this is the frequency that we're looking at. I'm going to rewrite it here, where frequency is equal to 1.031 times 10 to the 8. And they say it's seconds to the negative. I like to think of that instead as a per second, which is equal to hertz. Okay, hertz is just a per second, 1 over seconds. Now, there's a relationship between the wavelength and the frequency. So the frequency is really, since a wave travels, light travels in this wave that goes up and down, up and down, up and down. We can look at the distance between the peak and the peak, and we can say that that is lambda, the wavelength. It's the length that the wave travels before it repeats itself in that oscillation. And if we count how many of those oscillations happen per second, we get a frequency. So really, we can look at the speed that it travels divided by the wavelength, the distance from peak to peak. So I can say the speed of light divided by that wavelength. That's really the frequency that we're talking about. And we can calculate that because in a vacuum of space, or any type of vacuum environment, light travels at a constant speed. When it starts going through other objects like air and stuff, it does slow down a little bit, same with things. But for the most part, we can say the speed of light is constant, assuming it's traveling through free space. So we call that C usually. This is usually C over lambda. Lambda is this Greek symbol, and it usually is referring to the wavelength of something. So the speed of light, C, is equal to approximately 2.998 times 10 to the 8th power, and that's in meters per second. So that's pretty fast. It's going really fast when it comes down to it. It still takes about 8 minutes or so for light from the sun to reach Earth, even at that high speed. So it does actually have some travel time when you look at the astronomical parts of it. But when you look at it from a local scale, it's moving incredibly fast. The wavelength that we're looking for then, we can calculate because we know the frequency. So we can rearrange this equation here to solve for the wavelength. Now the simple way to do that is to just flip these two, swap the frequency and the wavelength in there. Really, you're multiplying by the wavelength on both sides, you're dividing by the frequency on both sides. But the basic idea is we end up with lambda is equal to C over frequency. And we can look at the units for that. The units of C is meters per second. frequency is just 1 per second. And you notice that seconds are in the denominator on both the top and the bottom, so they cancel out. This is going to give us something in the units of meters, which is what we're looking for. So that's a wavelength. So we can do the math on this now and say the speed of light is 2.998 times 10 to the 8th power in meters per second. I'm going to divide that by 1.031 times 10 to the 8th power in per second. So again, unit-wise, the per seconds and the per seconds cancel out. Even the 10 to the 8th power, those cancel out because they're the same value there. And then we're left basically with this 2.998 divided by 1.031, and the answer to that will be in meters. So let's go ahead and do that. 2.998 divided by 1.031, and that's going to be equal to 2.908. 2.908. I'm going to keep it to 4 sig figs because we've divided the whole time, and the value we were given was in 4 significant figures. The speed of light really is, you can go out to more significant figures than that. I just rounded it at 4 because that's what we were sticking to, and that's going to be a constant value. There's no uncertainty essentially with that. So I rounded my digits or my significant figures to be equal to 4, since that's what we had other in the problem. And that's going to be in meters. So that's about a 3-meter wavelength. So these radio waves are actually traveling at these huge wavelengths where they're arcing back and coming down. And that's about the height of me, even close to 3 meters tall. So that is going to be the length of those wavelengths in meters. This next problem, we have heated lithium atoms, which emit photons of light with energy of 2.961 times 10 to the negative 19 joules. So that's a tiny bit of energy when you think about it. It's pretty good because each photon carries that amount of energy. So when we look at light, or when we see light coming from something, we're not seeing individual photons. We're seeing like a bunch of photons all kind of stacked on top of each other to light something up. So we want to here calculate the frequency and the wavelength based on that of one of those photons. And then another question is, what is the total energy in 1 mole of these photons? Remember, 1 mole is just 6.022 times 10 to the 23rd amount of something. In this case, amount of photons. And the last question they ask here is, what is the color of light emitted? So there's 4 questions we really have to work out here. But the first one here is to tell us the energy. And the energy and the frequency are related through a basic equation. This is the energy is equal to HF, where H is equal to Planck's constant, and that's equal to 6.626 times 10 to the negative 34. And the units on that is joule seconds. So joules times seconds. And that constant revolutionized the world of physics and chemistry because it really was able to define energy per photon in this way. So we can utilize that to solve for frequency, because now that we know the energy, which is up here, per photon, and this is the energy of a single photon, we can solve for the frequency. So let's do that. Change to colors here. 2.961 times 10 to the negative 19 joules. And one thing I should do first, I like to rearrange my equations using variables first. So we can see I can rearrange this top equation here by saying E divided by H, this energy divided by Planck's constant, is going to equal my frequency. So that I can utilize that now. But I just wrote my energy down below. I can divide that by 6.626 times 10 to the negative 34 joule seconds. And if we look at the units for that, joules are going to cancel out. They're on the numerator and the denominator, but seconds are still on the bottom. So it's going to be a per second, which is hertz, which is a frequency. So our units they match. which is good. So doing the math on this, that's 2.961. I'm going to use this little e for times 10 to the negative 19. I'm going to divide that. I need my parentheses here when I type in 6.626. And I'll use e to the negative 34. That's our Planck's constant. And we are left with 4.468. Yeah. Or really 4.469. And that's times 10 to the 14 hertz, or per second. So that's our frequency. So, but they're not asking us for the frequency. They're asking us for, or they are asking for the frequency. So that's this frequency. We will also need to find the wavelength. Is where I was going with that. So to find the wavelength, so that frequency is going to equal the speed of light divided by the wavelength. So now we can rearrange and solve for that wavelength. So remember that wavelength is equal to the speed of light over the frequency, which in this case is going to equal 2.998 times 10 to the 8 meters per second divided by this frequency that we just found out, 4.469 times 10 to the 14 hertz. I'm going to write that as per second so my units cancel proper. So per second. And then I can cancel my units, which makes me happy. So we can plug that into our calculator now. 2.998 e to the 8 times 10 to the 8 divided by, need my parentheses on the bottom so I make sure I'm dividing by not just the 4.469 but the times 10 to the 14. I'm actually going to grab the value in my calculator and paste that in. That way I don't have that rounding error that might come up. Close my parentheses. So my wavelength is equal to 6.709 times 10 to the negative 7 meters. And that's pretty small. We like to talk about wavelengths in nanometers, which is usually the common visible range and spectrum of things. So we want to convert this to nanometers just to be more consistent with what we talk about. So to do that, I can use my dimensional analysis. I'm going to multiply this by 1 nanometer divided by, and nano is the prefix for 10 to the negative 9. So I'm going to put 10 to the negative 9 meters. Notice everything in this fraction here still equal to 1 because the units of 1 nanometer is equal to 10 to the negative 9 meters. So I'm not changing this value, I'm just changing the units of it. Meters are going to cancel out there, and we are going to be left with 670.9 nanometers. Because really when we do this math, 10 to the negative 7 over 10 to the negative 9, we just subtract the exponent from, we subtract the exponent on the bottom from the exponent on the top. Since that one's negative, it's going to be negative 7 minus a negative 9, so it ends up being 10 to the second power. So I'm just moving in that decimal place over ultimately 2 places to the right. And we get this 670.9 nanometers. Now we can use a kind of a chart of the spectrum to determine then what is the color of light emitted based on that. I'm skipping the mole just for a second. I'm going to come right back to that. But right now we want to look at what is the color of light emitted at 670.9 nanometers. And we're going to be approximate in this. So down here below, this is kind of the full spectrum that we know of, right? Everything from about really big wavelengths to really small wavelengths. The visible spectrum is just this tiny little area in between here, okay, which breaks up into the visible light, anywhere from about 400 nanometers to 700 nanometers. If you have really good eyes and you're looking in the dark for a while and you're adjusted, you could probably see a little bit past here to 750, 800. And you can probably go down a little bit more to like 380 or so here to see a little bit more of the ultraviolet. But for the most part, those UVs and the IRs, once you get 1 order of magnitude greater than this, you're not going to see it. Our eyes just are not built for those spectrums. But we have 670 nanometers. So looking at this, well, it's higher than 600, less than 700. Halfway would be about there. I'm going to go a little bit more and say that's there. That's a nice red light. That's visible to our eyes. We could see it. It'll be a nice red colored light. Now, we can then determine this here. They gave us the energy of one photon. They wanted to know what is the energy of a mole of photons. So 1 mole of photons is going to be equal to Avogadro's number, 6.022 times 10 to the 23rd, basically photons per mole. And really, I can say 1 mole of photons times that is how many photons there are per mole, times 2.961 times 10 to the negative 19 joules per photon. I wrote in a few extra units there, but really it's so we can cancel out my photons. I can cancel out my moles, and I'm left with joules. So we can plug that value in. 6.0, 6.022 e to the 23rd times 2.961 e to the negative 19. We have 1.783 times 10 to the 5 joules. So you see, it went from a tiny little bit of energy, that 10 to the 19th power, which is, 18 zeros, or decimal place 18 zeros, and then 2961, up to 1783, and then followed by 3 zeros. So that's quite a bit of energy. If we can even convert that to kilojoules by moving this decimal place over a bit, and we would end up with 178.3 kilojoules. So 1 mole of photons, the photons really carry a lot, and it's a bunch of little energy packets basically hitting things that give you all this energy. The next problem we have is when rubidium ions are heated to a high temperature, they create 2 lines in their spectral lines, or observed in its line spectrum at wavelengths of 7.9 times 10 to the 7th and 4.2 times 10 to the 7th. What are the frequencies of these 2 lines? What colors do we see when we heat rubidium compound? So there's 2 different wavelengths they're giving us that we're seeing those 2 lines at. We want to know what those frequencies are. Well, as we said earlier, the frequency is related to wavelength. Let's see over lambda. And here they're giving us lambda, those wavelengths. So we can just apply this frequency, say A to wavelength A is going to equal 2.998 times 10 to the 8th meters per second. We can divide that then by the 7.9 times 10 to the negative 7 meters, and see what that equals. 2.998 times 10 to the negative 7. We're going to divide by 7.9 times 10 to the negative 7. I forgot to put my parentheses in, so let's throw those in before I say okay. And this is equal to 0.079. That's the frequency. Per second. Did something wrong there, didn't I? What did I do wrong there? Should have had this instead of the -7 to the 8th power. That's what I did wrong there. I had my speed of light wrong. So let's recalculate that. So it's 2.99 times 10 to the 8 divided by 7.9 times 10 to the -7. That looks better. 3.795 times 10 to the 14 power. And that's in hertz. I should really be rounding this to 2 sig figs because the value I was given in wavelength was 2 sig figs. So that's 3.8 times 10 to the 14 hertz. Let's move this over. There we are. So that was for part A there. For B, it's going to be equal to 2.998 times 10 to the 8 meters per second. We're going to divide now by the 4.2 times 10 to the -7 meters. This just changes to 4.2. We still have the right exponents. This is equal to 7.13. Say it's a 7.1 times 10 to the 14 hertz. So based on those wavelengths, we were able to see these are the frequencies of those two lines. And we want to know what is the color of those. What color do we see when we heat this rubidium up? So we have the wavelengths already that they gave us. So let's convert those into nanometers, and we can then determine what color those are based on the spectrum. So that's 7.9 times 10 to the -7 meters. I can multiply that by my nanometer conversion. That's 10 to the -9 meters. Unit-wise, this is going to cancel out. And I'm going to be left with 7.9 times 10 to the 2 nanometers, which if we move that over, it's about 790 nanometers. Doing that to the second part, that's 4.2 times 10 to the -7 meters. Multiplying that by my conversion, nanometers per 10 to the -9 meters. That's going to equal 4.2 times 10 to the 2 nanometers, which is equal to 420 nanometers. So when we compare this onto our spectrum now, I got my spectrum down below here. We can see 790. It's going to be like a deep red color, and it's actually going to be infrared. It goes into this IR. Maybe if you, like I said, if your eyes are really trained to it, you might be able to see it very faintly, but most of us are not going to pick up on this really well, especially with all the light pollution and stuff going on around us. If your lights are on, you're not seeing this really well. The other color, 420 nanometers, that's going to lie more in this blue realm, or really, I'd say a darker blue realm, almost to violet, way over here. It's about 420 nanometers. So that's going to be like a bright blue violet light. And that's our eyes are really good at picking up on these. So we're going to see that one really well. So if you were to look at heated up rubidium, basically, the color you're going to see off of that is that bright blue color. This one here at 420 nanometers. That IR is just going to be too faint to really pick up, especially being drowned out by that 420 nanometer light. If you had a prism and you split it up, you might be able to distinguish that IR a little bit better, but without that, without splitting up the light waves, you're really just going to see blue light coming off of this. That leads us to the eyes of certain reptiles, because they pass a single visual signal to the brain when these visual receptors are struck by photons of a wavelength of 850 nanometers. So 850 nanometers, like I was saying, that's over here in the IR range. That's beyond the 720 we had here. So they can see a little bit more into that infrared. They can kind of see that heat signatures of animals. So if a total energy of 3.15 times 10 to the -14 joules is required to trip the signal, so that's our threshold signal, we need that much energy to make that work, to make that signal kind of trip in their head. What is the minimum number of photons? So first we can figure out, well, how much energy does a single photon take or give us? So remember that energy is equal to Planck's constant times the frequency. Well, we don't have the frequency, but frequency is related to the wavelength and with the speed of light. So I can say that's also equal to hc over lambda. So utilizing that feature, we know what the wavelength is of this light that we're talking about. We know what the total energy is. That's how much is required. But we know what the wavelength is, and we know what the speed of light is. We know what Planck's constant is. So in this case, the speed of light and Planck's constant are constant values, so we can calculate the energy of a single photon. So that would be 6.626 times 10 to the negative 34 joule seconds. That's Planck's constant, times speed of light, which is 2.998, times 10 to the 8th meter per second. I'm going to divide that whole thing by 850 nanometers. I'm just going to write this as in meters as times 10 to the negative 19 meters. It's not quite proper scientific notation because I have 3 places to the left of my decimal place, but it works. It's an easy, quick way to transfer nanometers into meters by just making it times 10 to the negative 19. And we can then make sure unit-wise, seconds, meters will all cancel out. We're going to end up with joules. Joules is a unit of energy, so we're probably good there. Let's do our math. So that's 6.626 times, let's use my E, times 10 to the negative 34. I'm using for that. I'm going to multiply by 2.998 times 10 to the 8, and then divide by 850 e to the negative 19. And this is equal to 2.337 times 10 to the negative 9 joules. So that's how much energy a single photon of 850 nanometer light has. But this signal in these reptiles' brains, they don't trigger until they have 3.15 times 10 to the negative 14 joules is required to trip the signal. I feel like I'm off by a factor of 10 somehow. E 10 to the 19. No, I'm good. I think I was off before. Okay. Oh, I am off. I'm way off. That should be 10 to the 9. It's not 10 to the 19 for nanometers. It's just 10 to the 9. So, yeah, that should give me the right answer, 10 to the 19 here. It's getting ahead of myself in my brain. I knew something had to be off because the amount of 1 was going to be greater than this. So now to find out how many photons we need to trigger that ability, that receptor that he has, we can just divide that 3.15 times 10 to the negative 14 joules divided by our 2.337 times 10 to the negative 19 joules. Unit-wise, that should cancel out. So we should have a unitless thing, essentially. It's essentially a number of protons we're looking for, but it should just be a number. And now we can divide. So 3.15 e to the negative 14 divided by parentheses, this number up here. There we go. This is equal to 1.348 times 10 to the 5 photons, we'll say. So that's how many photons need to hit that reptile's eye for it to trigger this ability that it has, triggering this signal, which is quite a lot of photons, but in the world of photons, it's probably not that much. All right, the photoelectric effect. So the photoelectric effect is an effect where when light hits a plate of metal or some type of metal, it's able to transfer its energy to the electrons in that metal and free the electron from the grasp of that metal. So it essentially launches an electron away from the metal. I can draw a little picture here. This is my metal plate. I have some wavelength of light coming in, and it strikes it. There's going to be a bunch of those, essentially. So when it strikes that, if it transfers enough energy from it, if the wavelength of light has enough energy in it, that photon hits the electron, transfers energy to it, that energy can make it free that electron from there and actually propel it away from the metal with some type of kinetic energy. It's kind of physics 101 here. So we call this that energy of light, which is equal to HF. And we can say that the energy that is light that's transferred in would be equal to the kinetic energy, the energy given to the electron and that's moving. So it's the energy of motion, essentially, plus the energy it takes to release it from the bond of the atom, to release it from the metal itself. We call that a work function. I'm going to use that, the phi character there. So this here is my work function. So that's the basic idea. So if you had enough light, one photon of light were to hit that metal and it had just enough energy that was equal to the work function, it would free the electron from the metal, but the electron wouldn't go anywhere. It wouldn't have any kinetic energy to move. It would just still be, it'd be pop, and then it would absorb back in. But if we give it a little bit more, it would go boom, and it'd shoot out of there. And in the photoelectric effect, they specifically put a voltage potential there to slow down and stop the electrons from moving and pushing them back into the metal. It was a way for them to test the work functions of the different metals. It was a way to also verify the idea of this Planck's constant. I won't go in too deep into all of that. But what we can do is utilize this equation here to kind of solve for what we're doing here. Because here it tells us that they want to know what the threshold frequency for sodium metal is. So like at what frequency of light do we start to eject electrons from things? So they give us an example. If we have a photon with this frequency, 6.66 times 10 to the 14 hertz, they tell us that we've observed an electron being ejected with this much kinetic energy, 7.74 times 10 to the negative 20. So they're telling us the kinetic energy, and they're telling us the frequency, and we can use that to kind of determine what that work function is, because the difference in energy between the energy of the light of that frequency and the kinetic energy is going to equal that work function. So we can rearrange this equation. So I said HF is equal to KE plus phi, the work function. We can just subtract KE from both sides. We have HF minus KE is going to be equal to that work function. So we can do that to solve for that work function. And that work function is going to be in energy, in joules. And we can utilize that to then say, well, what frequency of energy is necessary that provides us with the same amount of energy as the work function? And then solve for that threshold frequency that they're talking about. So let's do that here. We have So H is 6.626 times 10 to the negative 34 joule seconds. The frequency they gave us is 6.66 times 10 to the 14. That's going to be per second. And then we're going to subtract from that the kinetic energy they gave us, 7.74 times 10 to the negative 20 joules. Notice, unit-wise, I always like to point out the units. The seconds are going to cancel out. You're going to end up with joules on this first term, which matches the joules on the second term. You can't subtract two terms together unless they have the same units together. It's very important. So if you have the different units, you can't just say, oh, meters minus seconds. Doesn't work. It needs to be joules and joules, the same units. So let's see what this equals. 6.626 e to the negative 34 times 6.66 e to the 14 minus 7.74 e to the negative 20 . And I've got 3.639 times 10 to the negative 19 joules. So that's the energy of the work function. That's how much energy it takes to free the electron from the metal, but then we have to take it one step farther and turn that energy into a frequency. Because this is going to equal the energy of some light, some frequency of light. So what is that frequency? So to find that out, we just divide by h. Divide everything by h, since it's an equation and everything's equal. Those go away and we can solve for frequency. So remember, h is 6.626 times 10 to the negative 34. We can do that. Grab this, divide by 6.626 e to the negative 34. That's our Planck's constant. It's in joules second. Notice, joule seconds, the joules will cancel, giving us per second, which is frequency, a hertz. We're left with 5.49. What units? Yeah, 3 sigs. Times 10 to the 14 hertz. That is what they call the threshold frequency. Anything less than that doesn't have enough energy to really go anywhere. The electron's still bonded to the metal. Anything more than that, the electron is released from the metal, and if you go significantly more, it's actually propelled quite a distance away. So you can actually send electrons kind of radiating out from all directions. And if you create a electric potential, you can attract them with that. But that's beyond what we're doing here. We're just trying to look at what is the energy of the light itself and how can we correspond it to frequency and wavelength. Those are the key aspects of this chapter. The last question they ask here, will the photoelectric effect be observed if sodium is exposed to orange light? Well, so this frequency here, we can relate that to its wavelength. So wavelength, we said it's equal to c over frequency. So to do that, do the math. That's 2.998 times 10 to the 8 meters per second divided by that 5.49 times 10 to the 14 hertz or per second. Lost my calculator. Let's bring it back. There we go. 2.998 e to the 8th power divided by, I had it just right up here. Let's use it. This is equal to 5.458, 459 times 10 to negative 7 meters. Converting that into nanometers, it's going to be 545.9 nanometers. Just multiplying it or dividing it by 10 to the negative 9. Moves that decimal place 2 to the right and turns our units into nanometers. I think we had 3 sig figs too, so technically, gotta watch your sig figs. Well, there we are. 546 nanometers. So where does that fall on our spectrum? Here's our spectrum here. We can use this one. 546, that's about 550. So it's like right in the middle of that guy. Ignoring what I wrote here from the last problem. This is our, I'm thinking, yeah, 546. 546 nanometers. So it's like a greenish yellow light is what that is. The orange light, that orange light falls over here. Remember, going this direction, it's lower energy. Or if I go up this direction here, this is higher energy. The shorter the wavelength, the higher the energy. The higher the frequency, the higher the energy. The shorter the wavelength, the higher the frequency. So here, since we have this and the orange light is over here lower in energy than our 646 nanometer threshold that we have, we can say that orange light is not going to do that. Orange light is not going to expel any electrons from there. I'm over here. So will not produce the photoelectric effect. Just because it's lower in energy than the threshold frequency that we're looking for. So now we're going to get into the Bohr model. This is the only one we're really going to tackle on the Bohr model. So they say using the Bohr model, determine the energy of an electron with n equals 6. So if you go through the equations that Bohr did, he had a pretty basic model of the atom. It was one of the first, close to being correct models. He was slightly wrong in various ways, but he knew that, but it was better than all the other ones. And he had the solar system model, where we have our nucleus in the middle, and we have these kind of orbital rings that go outside. And the one thing he really had correct was there are discrete paths that the electrons can be in. He had them in rings, so this would be like n equals 1, 2, or 3, depending on how far of a radius it was against that. And he had an equation for the energy of the energy of the electron based off which orbital it was in. What that equation is, E is equal to negative k z squared over n squared. And in this one, k is equal to this constant 2.179 times 10 to the negative 18 joules. Z is the number of protons, whatever atom it is. So here we're talking about the hydrogen atom, which is the first one on a periodic table, so that's going to equal 1 for us. If we were talking about a carbon atom, that would be 6, and so on. And here they're giving us n, and it's equal to 6. So really, this is just recognizing the different patterns of it, which equation to use, and then plug and play. And this tells us the energy of an electron in the 6th orbital, kind of away from the hydrogen. And remember, hydrogen has 1 proton, 0 neutrons, and it has these rings. Let's see, 3, 4, running out of space. 5, these are supposed to be circular, 6. So we have an electron way out here. So it has a lot of built up energy in it, where it's going to eventually drop down to that lowest orbit where it wants to be. And when it does that, it releases energy outwards. And that energy gets released as a photon, as a light. So that becomes these transition patterns. When we excite these electrons and we let them relax, when they relax, they release the energy back out in light. So they absorb the energy, then release it. But we can calculate that energy based off of this. So let me ditch all that. So plugging these in, negative 2.179 times 10 to the negative 18 joules. And we're going to multiply that by 1 squared. Divide that then by 6 squared. Plugging that in to our calculator, 2.179 e to the negative 18. That's in joules. Multiply by 1 squared. 1 doesn't really matter because it's just 1. But we can divide then by 6 squared. And this is negative 6.05 times 10 to the negative 20 joules. So that's the energy of a single hydrogen atom, of an electron at the 6th orbital. When it releases that much energy. And we could actually even figure out then when it releases what would the wavelength of that energy be, what would the frequency of that energy be, based off of that previous calculations we've been doing. But they're not asking for that. So that's basically this. That's how much energy is in an electron at the n equals 6 of a hydrogen atom. Now we go on to these subshells. And there's a lot of fun things with subshells. It gets kind of confusing, and it takes a little bit getting used to. But in reality, they want to identify which electrons are in the following quantum numbers. So remember, n is the orbital that they're in, whether they're in the first ring of orbitals, the outer second, third, fourth, fifth, sixth, etc. And that can go on to infinity. L is kind of the angular momentum that it has in there, and that helps determine kind of which block of electrons we have. So if we switch over to our periodic table, we can see the L group determines whether or not it's going to be, in the D block, the S block, the P block, and so on. So if we had, everything over here in the S block, that's L equals 0. Everything here in the P block is L equals 1. Everything here in the D block, it's L equals 2. The F block down here, it's going to be L equals 3. And we don't currently know of any atoms that are up into L equals 4, L equals 5, or bigger than that. That covers the entirety of the periodic table that we know of. In fact, everything that gets kind of up here, all these guys, they're so reactive that they decay almost immediately. They're not stable at all. So although we can create them in a laboratory in isolated environments, they quickly appear and then disappear, and they come down and become smaller elements on the periodic table. So really, L equals 1, 2, 3, and that's all that we really need to pay attention to. Anything beyond that is kind of, we don't have an element that fits that category just yet. We haven't discovered it, at least. But we can utilize this then to, jump back over here, determine the subshells. So it's the S subshell, P subshell, D, F, G, and so on. So for the N's, that's not going to affect the subshell, or it's just what layer of subshell it has. In this case, the L equals 2. As we said here, L equals 2, that's our D block. So that's our D subshell. L equals 0, that's going to be our S subshell. L equals 3, that is our P subshell. No, I'm off. I'm sorry, I went 2 is P, 1 is P, 3 is F. The F subshell, those lanthanides and actinides. So going back, 3 is F, 1 is P, 2 is D, and so on. And these also relate to the different energy states of the electrons that are in there. Problem 44. Well, before I go on, actually, there's one thing I wanted to show here. So to get more of a visual on what these electron shapes, I have this cool simulation on my iPad. I'll pull up here. Kind of zooms in. Comes in sideways, which is odd. Okay, so all the numbers are going to be sideways, but the graphic will still be there. This is an S subshell. It's just spherical. It has that shape. I can kind of rotate it, but you can't really tell that I'm rotating it. If I were to increase, these numbers here are my N, L, and M subshells, my quantum numbers. So if I can increase the quantum number here, you can see that now there's two S subshells. The yellow one is n equals 1, the blue one is n equals 2. And there's this void, that node in between, with no electrons really fit in there. They're kind of repelled by the inner electrons. So the n equals 2 electrons are floating out there. We can think of this as your 1s2, 2s2 electrons in this case. Now we can also add, I just increased L by 1. So now we have our p orbitals, L equals 1. So the p orbitals are just kind of floating on either side of the two. When this is n equals 2, L equals 1, I can increase to n equals 3, L equals 1, and we see it's that same pattern, but now there's different rings of those two different kind of weird orbitals kind of floating around there. We can rotate it around, see it from different angles. If I increase to L equals 1 now we get this type of pattern. Excuse me. So this pattern here is saying that L is equal to 2, N is equal to 3. That's another type of angular momentum. Just to show you kind of the electron configuration, what those electron groups are kind of doing in this category. And we can increase M as well, but we're not going to go too much into that. And it gets a little bit more fuzzy to really pay attention to what's worrying about. So each of these orbitals that we're looking at for N and L correspond to different things. So we can increase N dramatically to see it gets more complicated, but it's the same basic pattern that's happening. We still see that same figure in the middle. There's just more nodes and more rings and bigger distributions of electrons floating out, but it's following that same similar pattern. If we increase L, we can see the different complexities that happen with that. The different rings of those as well. It's following a very similar pattern in a way. It's very complicated. It takes a lot of math. If you're really interested, look up the Schrodinger equations. You can see them sideways on my screen. These are all calculated using the Schrodinger equations, which is a multivariable differential equation. We can see this graph in the middle here. I know it's sideways, but each of those humps as it goes down to 0, those are kind of the probability, and it might be easier if I get rid of all of these. So now we have those nodes there, and you see each of those little humps as it comes down and reaches the bottom of that graph. That's the probability of an electron being at a certain radius. So when that probability reaches 0, we get this node, and that defines the different subshells, the 1s, 2s, 3s, 4s, 5s, and so on. It's a really fun program to play with. This is called Atom in a Box. It was a free download on my iPad. If you have an iPad or something like it, definitely check it out if you are interested more in what's going on here. This is version 1.1 of Atom in the Box, you can see here. Anyways, I digress. There we go. So number 44 here is really asking us which of the following equations describe particle-like behavior and which ones describe wave-like behavior, because electrons can act as a particle and a wave, and sometimes they have more particle-like properties, sometimes they have more wave-like properties, and we can distinguish that based on the type of equation that they're using for it. For this first one here, this is saying C is equal to lambda times V, which is really, V is really new. It's a Greek letter. Looks like that. Looks like a V. I hate using it. I always use an F because it's really frequency in there. So they're saying lambda times frequency is equal to the speed of light, which is true. And it's true specifically for waves. So I would say that's wave-like behavior. The next one, E is equal to mv squared over 2. This is our kinetic energy formula. If you were to launch a cannonball or shoot a bow and arrow, and you could calculate the energy that object has, that projectile has, based on its velocity, this is the equation to use. This is a kinetic energy equation. Energy of motion, and we call this particle. There's no wave-like properties that we're really mixing into that. This next one, this is the Bohr Radius. This is what that program was kind of calculating, but on a much more complex level. So this tells you the radius of an electron configuration of that electron ring, where n is equal to some electron energy state. A is the radius of 1, and z is the proton numbers. But this deals with particles. Because Bohr didn't really think of his electrons acting as waves, he treated them all as particles. This next one, this equals HF, so that's what I've been using, where it's the frequency, and this is the energy of a light wave. Now, this H really helped bridge the gap between particles and waves. So this corresponds to both this uniform wave and property duality that's happening in physics at that time. So anytime you see that H in there, it's accounting for the dual nature of particles and waves. So the same can be said down here for this. This is really the de Broglie wavelength. If I can spell, it starts with a D. De Broglie wavelength. And de Broglie was the first person to come up with this idea that matter particles can also travel as waves, similar to how light travels in a certain way. And he utilized this type of equation to define the wavelength of an object based on its mass, velocity, and Planck's constant. So that would also be a both. Got the particles. So those are a lot of the equations you're going to use when you're talking about these types of things and what the situations are for them, how those are behaving. This is the last one I really want to deal with here. Write a set of quantum numbers for each of the electrons in an n equals 4 in an Se atom. That's selenium. Yeah, I always pronounced that wrong, but I think I got it right. The selenium atom. So the selenium atom, we can write that electron configuration out. So looking at our periodic table again, I'm going to erase some of this stuff. We have those L numbers. But here, really, for the electron configuration, group 1 and group 2 are your s orbitals, right? Groups 3 through 12 down here are basically your d orbitals. 13 through 17, or 13 through 18, really, minus helium, which goes over there, are going to be your p orbitals. And they're separated out by rows. So if we're talking about this row here, we're talking about the 2p orbitals. Over here, we're talking about the 2s orbitals. Down here, it's the 5d orbitals, and so on. And you will notice when you look at this periodic table, the 3d orbitals are really on the 4th row, because the 3d orbitals, although they're farther inside than the 4s orbitals, they are a higher energy state than the 4s orbitals. So the 4s get filled first before the 3ds. And then the 3ds get filled next after the 4s before the 4p's. So it's a little confusing, but once you get used to it, it's not too bad. A similar thing happens down here with these 4f orbitals here, because these are really plugged in to this area here. You can expand the periodic table out to account for that. But when we're looking at selenium, that's this guy over here. Notice it's in the 4p orbital, and it's 1, 2, 3, 4 places up. So we would say that's 4p4 for a standard selenium atom. So we can write out that equation to begin with, or the configuration there. So let's do that. Be a 1 s2, 2 s2, 2 p6, because there's 6 electrons in these p orbitals over here. We're at 3 s2, 3 p6. Notice we skipped the 3ds because they're on the 4th row. They don't come in until the 4th row. We then have a 4 s2, 3 d10, 4 p4. So that is the electron configuration for those for selenium, Se atom. We want to define what are the quantum numbers for this, right? And if we look at this configuration, we can see the s orbitals. I'm going to draw those in red. Those 3, 4, there we go, another one. Those are all n numbers. N equals 1, n equals 2, n equals 3, n equals 4. Let's see, the p's, that's this one, and this one. Those are all L, right? And those are all going to be L equals, I'm sorry, I should say, oops. I was right in saying that they're all N, but really it's also L is equal to 0. Because for any electrons in there, the angular momentum of there has to be a 0. Because s orbitals can only have L equals 0 in them. L orbitals for the p shell can have L equals 1. And last is these d orbitals here would be L equals 2. But we're looking for, we're going to write the set of quantum numbers for each of the electrons in the n equals 4 Se atom. So really we're just looking at the 4 numbers. So all of these other ones here, all these 3s we can ignore. We really just want to look at what is the 4s2, 4p4 electrons. What are the quantum numbers of those? Focusing just on that n equals 4. So let's do that. I'm going to write a little table here. So this table is going to have, give me 3 lines. So there's, besides the N, L, we also have M and the S. So they just represent different possible quantum numbers. Remember that N can be any positive number from 1 up to infinity, but L needs to be up to n minus 1. So if n equals 4 in this case, you can't have an L of 3. You can only have that L of up to n minus 1. And in this case, since we're only dealing with S and P's, L is going to be either 0 or 1. Now M, it can be the same as L plus or minus. So in this case, let me change this now to be this. Here is going to be 0 or 1. So M is going to equal plus or minus 1 or 0. It can't go greater than L, but it can be equal to L, but it can also be negative. S, this is really the spin of your electrons, which is either a positive 1/2 or a negative 1/2. And for each electron configuration can have both an upspin and a downspin, essentially. But they like to spread out. So until all the upspins are filled, you don't get any of the downspins in that orbital. So now we can start populating this table a little bit. For the 4s electrons, there's going to be some 4s which have an L of 0. When they have an L of 0, they're going to have an M of 0, and it can have a positive 1/2 spin. Okay, so that's that first electron in the 4s. The second electron in the 4s still has an L of 0. It has to. M, therefore, also has to be 0, but it's going to have a down spin. of -1/2. Then we're going to have the first one in the P group, which has L equals 1. It's going to have an M of 0. We're going to have a +1/2 on there. But like I said, all of them are going to be positive until we have everything filled up. And there's 3 different M groups, right? So you can have a 0, you can have a -1, and a +1. Each of those is going to have an L equals 1. It's a P orbital. And each of those is going to have an N equals 4 because that's what we're looking at specifically. This is the N equals 4, L equals 1 now, and then M changes from 0 to, I'll put a little line here even. These are kind of the ones with L equals 1. 0, -1, and 1. So each of those can have a +1/2. But notice we had 4p4. We have only gotten 3 of the electrons, right? 1, 2, 3. Those are just 3 of those electrons. We need to add 1 more. So by adding 1 more, I have that 4. Still has to be a 1. But now we can say, go back to that 0, that lowest energy state, and make it a negative spin. And those are all the possible quantum numbers of the selenium atom, or selenium electrons, where all of them are going to be the same spin. They could be positive or negative. We like to say positive first, then negative. But really, it's a matter of perspective, so it doesn't really matter. But all of them will be positive until that electron filled. Notice we filled this one with a negative because those 4s electrons fill first, then the 4p electrons fill. And that is all I have for you. We'll leave you with a fun little meme that I found about this, where someone asked to caption this photo. Someone said 1s2, 2s2, 2p6, 3s2, 3p6, etc. Have a wonderful day. I'm going to jump into the Pingy drop-in tutoring, so if you have any questions, definitely check me out there and ask me any questions you want at all. And if not, I will talk to you next week. Have fun.